All right, Oaks, Thursday 2nd. Sorry I'm not here, so we are going to take some notes today. And the title of today's notes is Coulomb's Law. You can get the spelling right there. And there's an exit slip quiz on Google Classroom. So it's 5 questions. Make sure you answer everyone seriously because it is going to automatically grade it and put a grade in the gradebook for you. They should be easy if you are paying attention. So let's go. Let's do it. All right, so we yesterday started zapping things. We started talking about electrical charges moving. So electrons moving, for example, onto the balloon when I rub the balloon on my head. We call that charge. The amount of charges, electrons or protons, the amount of charges is a quantity that we can measure. Because right enough, if I rub that balloon on my hair for longer, more electrons are going to transfer across, so that balloon is going to become more charged. So the quantity of charge, the symbol we use is a lowercase q, and the unit we use is the Coulomb, or capital C is the symbol, Coulomb, named after this fella, Monsieur Coulomb, who was a French guy, so that's why I'm saying it like that. Now, here's the funny thing about the Coulomb, the unit of Coulomb. I mean, when you think of 1 meter, I mean, it's like, you know, what 1 meter is like 3 foot, you know, it's like half your body height, right? 1 Coulomb is a huge amount of charge. Ridiculous amount of charges go into 1 Coulomb's worth of charge. Just for interest, I mean, so you know, the charge of a single proton, so the amount of measurable charge in a proton is 1.602 times 10 to the negative 19 coulombs. This is a tiny number. I've written out all the zeros for dramatic effect here, right? This is a tiny amount of coulombs, but the converse of that is, if 1 proton is a ridiculously small amount of coulombs, how many protons does it take to make 1 coulomb's worth of charge? And you do the math, it's 6.242 times 10 to the power of 18 protons. So 1 coulomb is a huge amount of charge. I know it's kind of hard to get a baseline on this, but the amount of charge on the bottom of a normal sized thundercloud is about negative 40 coulombs. The amount of charge at the top is positive 40 coulombs. And yeah, 40 is a big number, but it's not huge. I mean, I would expect like the amount of charge to be in the thousands or millions, but no, it's just 40, right? So 40, 50 coulombs, I mean, that's a deadly amount of charge right there. So as discussed, 1 coulomb is a huge amount of charge. And when we're dealing with just atoms or real small things, it seems silly to measure in such a big unit. So considering that 1 electron or 1 proton is the smallest amount of charge possible, because you've got to remember the electrons, the protons, they are what give things charge. So what we do is we actually measure that in what we call an elementary charge, where that same number I gave you before, 1 elementary charge is 1.602 times 10 to the negative 19 coulombs. So what we tend to do is we say a proton has 1 E, but an electron has negative 1 E, right? If I have 2 protons, then I have a charge of 2e. If I have 3 electrons, I have a charge of negative 3e. The ramification of that is it is only possible to have integer values of elementary charge. Integer meaning a whole number. You can have a charge of 1e or negative 3e or 5000e. What you cannot have is 3.6e. or 2.5e, because that would imply that you have somehow got a proton and cut it in half, right? Or you've got 0.6 of a proton. That doesn't happen. That doesn't work. That's not a thing. So you can only have whole number values of the elementary charge in any kind of calculation. So moving on, we want to talk about the force between charges, because there's a couple of variables that go into how much electrostatic force there is. We saw the electrostatic force yesterday, right? The force that forced my hair up towards the balloon, that forced all the people's hair apart from all the other hairs. The force that forced those those pie plates upwards, overcoming gravity. There's got to be a way we can measure that force. And it's got to be related on a couple of things. And I can actually demonstrate that in a little simulation. All right, this is a little simulation, PhET simulation, where you can see 2 charges. Charge 1 here is negative 2e. So basically we have 2 more electrons and protons. This one is a charge of 4e, so we have 4 more protons than electrons, right? And it shows you the force between them. Now, the first variable that I think is fairly obvious to increase the amount of force between them is just increasing the amount of charge. Let's say I double the amount of electrons, like rubbing the balloon on my hair twice as long or whatever. It goes from 1.15. If I double it, it is now 2.31. It is doubled. If I double 4e to 80, it goes from 2.31 to, oops, too much, 4.61. It doubles it. So there's a direct relationship there. But the other interesting one that may make sense is the distance. I can actually move these. I'm going from 2.31 newtons. Watch what happens as I move these closer together. You can make a prediction. Is it going to get bigger or smaller? Right enough, as I move them closer, it gets bigger, it gets bigger, it gets bigger, it gets bigger. But the funny thing is, the closer they get, it gets bigger quicker, right? This is a huge difference. And as they get real close, it gets crazy strong. Look at that. It went from 4 to 9 just in that one little increment there. So this all comes together in a lovely law called Coulomb's law. So your man Coulomb's law came up with the relationship between the electric force between charged objects, and this is the equation. The electrostatic force is equal to negative K sub C times Q1 Q2 over R squared. So what do these things mean? All right, K sub C is a number, Coulomb's constant, 8.99 times 10 to the power of 9 Newton meter squared over Coulomb squared. This is just a number that makes sure that when I put these values in as coulombs, this in as meters, it spits out my newtons there. Q1 and Q2, they're the charge of the particle. So like you just saw, if you had negative 4 and 6, you'll put negative 4 here and 6 here. Divided by the distance between them squared. This is in the denominator and it's squared, which means as the distance gets smaller, the electrostatic force is going to get bigger. Again, it's the electrostatic force, so it's in newtons, and as always, it's a vector. But a couple of interesting things to just point out here. Main one is it's negative. So why is it negative? It's not because he was just a negative person. It's because when you think about it, there are two types of force. You can have an attractive force or a repulsive force. Let's say, for example, I put in a positive charge here. Let's say 2 coulombs. Let's say I put a positive charge as Q2. Let's say 4 coulombs. 2 times 4 is 8, and then divided by whatever the distance is between them. They're both positive. It's going to be a repulsive force. So by having this negative here, my force is going to be negative. It's going to tell me it's a repulsive force. Let's go the other way. Let's say I have a negative 2 coulombs here. Let's say I have 4 coulombs there, negative 2 times 4. These two is going to give me a negative number, but because they're opposite charges, they're going to attract. So these two give me a negative number, multiplied by this negative is going to give me a positive value. That tells me they attract. So the final thing I just wanted to talk about was, does this equation remind you of anything? And the answer is, I hope it should. It should remind you of this equation here, which is the equation for gravity. You remember the force of gravity between any two objects is G, which is a gravitational constant, times mass 1 times mass 2 divided by R squared. The exact same geometry happens to cause this inverse R squared relationship. They're both field forces, so the force gets weaker as a function of an inverse square of their distance. The only thing is, this doesn't have the negative because gravity is only attractive, right? Gravitational objects only fly towards each other, but here objects can either fly towards each other or away from each other, depending on if they're positive or negative. The other important thing is gravitational constant, 6.67 times 10 to the negative 11. This is a tiny, tiny, tiny number, 0.0000000000667, I think. Coulomb's constant, 8.99 times 10 to the power of 9. This is a huge number, 899000000. It's a huge, huge, huge number. This tells you that the electrostatic force is way stronger. I'm not going to do the full calculation, but if you take the electrostatic force between an electron and a proton, as happens in a hydrogen atom, the number you get is 8.19 times 10 to the power of 8. If you take into account the average distance between them, which is a tiny distance, and the charges, one is positive, one is negative, of the electron of the proton, you get times 10 to the negative 8. If you were to think of what the gravitational attraction is between an electron and a proton in the same hydrogen atom, the mass of an electron is times 10 to the negative 31, mass of the proton is times 10 to the negative 27. I'm multiplying it by this tiny constant. I get a tiny, 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 tiny number. And the reason I'm telling you this is if you look at the ratio between the electric force and the gravitational force, the electric force turns out to be bigger. Not just a little bit bigger. If you take the ratio of the electric force to the gravitational force, the electric force is 2.27 times 10 to the power of 39 times stronger. It is way, 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 way stronger than the gravitational force. Gravity is a very weak force. Counterintuitive, but it is very weak. All right, that's me. It's 11 minutes. I was trying to make it 10. I apologize. You should be able to answer all 5 questions on the exit slip. And that is all I have to say for today. Have a good day, chaps. Take it easy. I will be back Friday and tomorrow, so I'll see you then. All right, wide out.